So today's class, I intend to make it kind of different because I think it's the last class. But first off, depending on how much you guys prefer, that would determine how much I would tilt. So I was thinking if you guys would prefer, probably we should go through previous topics first. Then maybe we can then go into the lesson for today. Maybe difficult topics that probably you feel I think I need an understanding in this point, or I need an understanding at that point, or I've been studying, and I think this topic is seeming very crucial. So that's one option, or I should just go ahead with the lesson, and maybe after the lesson, we'll then have the elongated talk. So which one will you guys prefer? Should I go on with the lesson, or you have questions probably that we could start with? Then once we've tried touching it a little bit, trying to simplify it, then we can go on with the lesson. Any response?
Sir?
Okay, I was asking, I said, I was thinking of doing this lesson in two ways. Either you people would propose a topic that maybe I should go back on, or I should just start the lesson. Then once we are done with the lesson, you will then bring topics that probably we having for next week. I don't know which one will be better for you guys. Okay, we should just start straight up. Okay, so let's head into today's lesson. So in this lesson, we'll be treating transition metals. Yesterday we were talking about the periodic table. So today's lesson, looking at transition metals. Then we'll also dive into environmental chemistry and nanochemistry. And towards the end, we'll look at organic chemistry. So I'll try to speed up on some of all these other ones, such as we would have time to look into organic chemistry a little bit more, because I think it's broader than the rest. So let's go. As I said, we'll be looking at these topics, and let's just head into the lesson straight up. So transition metals, one key factor that would help you understand or tell whether a transition metal or whether a particular element the transition metal is it is contained in the D block. It's contained in the D block. So this is one key characteristics of transition metals. They are always members of the D block. So all members of the D blocks are called transition metals. I think except a particular group that they actually called out, the lanthanide and actinide, they call them the inner transition metals. But the normal transition metals or the general transition metals, it's talking about every element inside the D block of the periodic table. So if I remember yesterday I said I tried drawing something. I think I tried drawing something like this, the periodic table, a simplified form of the periodic table. I said it's looking like this. We have a block here. No, this is we have a block containing two columns. We have a center block containing 10 columns, and we have the extreme block containing 6 columns, and maybe the last one having 14 columns. So the D block is the block in between. That's the center block of the periodic table. So it has 10 columns. So meaning the transition elements, they have 10 groups of transition elements. So these transition elements, they have this special characteristics of being able to have variable oxidation states. They have variable oxidation states. Like you can see, you hear copper having copper one, copper two. You hear something like titanium four, titanium two, and so on. Some of this manganese five, manganese seven, all those kind of stuff. So these are characteristics of these. As I was saying, I said the transition elements,
Yes.
they are members of the periodic table between group 3 and group 2. Between group 3 and group 2 on the periodic table. And these elements now, they have variable oxidation states. Like we know that we have manganese 7, we have manganese 4, and different other oxidation numbers of manganese. The same thing we have with copper 1, copper 2. So this is a characteristic that is popular with all transition elements, they mostly always have variable oxidation states. They mostly always would have variable oxidation states. Some of them don't have, but those ones are just because of special reasons. So, but mostly they would always have variable oxidation states or oxidation numbers. So they have high boiling point and they are very good conductors of electricity, as we can see in the case of copper, the most conducting element on the periodic table. So some of the common examples of these elements are iron, copper, zinc, and the rest, scandium, titanium, cobalt, manganese, and the rest. So let's move on. Sorry, we have that we are now moving into. We talked about transition elements, and I mentioned some key characteristics of this element. I said they have variable oxidation state, and now before I move on, I think I should mention that before I move on, they are known to have the outermost electron in the D block. If you're trying to write the electronic configuration to tell whether a particular element is a transition element, the last value of the electronic configuration, the last energy level of the electronic configuration will be on the D, even if it is 3D, 4D, 5D, but that last one will always be D. That's telling you that it is the transition element or is a member of transition element. It might be D, mostly it will be D. Then in some other special cases where you're talking about inner transition elements, it will then be F, because the F element or the members of the F blocks, they are also transition elements, but they call them the inner transition elements. And also they are also known as the lanthanides and actinides. So they're just like brought off from the transition elements and selected separately because of their similar, very, very close similarities due to the orbitals of some of the electrons that they contain. So these elements in group the transition elements. So they are another characteristic of them is that they are known to have different colors. They are known to have colors like zinc. You see the color of zinc. Cobalt has color of blue. Cobalt has color of copper has color of blue. They form colored compounds. Yeah, that's the better way to say it. They form colored compounds, different colors. Iron, you see, iron can be in green form. Normal iron, IRON. Of coordination chemistry, you're talking about a kind of the chemistry that deals with the study of ligands and metals. Ligands and metals. Probably if you are probably going to chemistry properly or trying to study chemistry in the university, so or maybe any advanced chemistry course, you might talk deeper in about this coordination chemistry. So these compounds, their coordination chemistry is the study of how metals and ligands they bond and how their arrangement is in space. So coordination compounds they consist of a central metal atom bounded or bonded to a ligand. So this central metal atom is always positively charged, while the ligand is always negatively charged. So now in coordination chemistry, I said it is talking about coordination compounds. So this one is very important that you take note of what I'm trying to say now. These metals they are known to have to be electron pair acceptors. Electron pair acceptors. They don't really share, like they don't really how these coordination compounds form is one of them, the ligand, donates a pair of electrons to the central metal atom. A ligand donates a pair of electrons to the central metal atom. So the metal atom just the only thing the metal atom does is it just provides space. It just has a vacant space. Once it has vacant site, ligands would find their way to attach to it. So usually the metals that usually form this kind of compounds are usually transition elements. They tend to form this kind of compounds very well, but it's not only them that is restricted to forming this kind of compounds. Lithium also forms that kind of compound in some cases. So typically, coordination compounds are compounds that are made up of a union between a central metal atom, sorry, a central metal atom or ion and a ligand. So ligands, they are known to be electron-rich species. They are known to be electron-rich species that donate lone pair of electrons. They donate lone pair of electrons, or they donate a pair of electrons to this central metal atom in a form of bonding called coordinate bonding. So the type of bonding that occurs in this coordination compound is called coordinate bonding or coordinate covalent bonding. So it's a form of covalent bonding, but it's called coordinate covalent bonding. So now these coordinate compounds or these coordination compounds, there is this characteristic about them that they kind of have unique structures. If you can remember when we were talking about the valence shell electron pair repulsion theory, these coordination compounds they tend to follow this particular form. So some of them they can be bonded to 6 atoms. They can be bonded to 4 atoms maximum. They can be bonded to 8 atoms maximum. But depending on how the number of atoms that is around them, you tell their coordination number. So I did not really write that here now, but take note that coordination compounds they always have a coordination number. Coordination compounds always have a coordination number, and that coordination number is equal to the number of ligands that is bonded to the central atom. The number of ligands that is bonded to the central atom or the central metal atom. So if they ask you what is the coordination number of a particular coordinate compound or coordination compound, what they're just trying to ask is check how many things are attached to this particular central atom. So in this case, now let's look at this. Let me go back a bit. Let's look at this one now. We have this one here. Sorry, this is my illustrator. We have copper, Cu, and it's bonded to ammonia. This one here, ammonia, NH3. It's bonded to NH3. And how many of NH3 is it bonded to? Four molecules of NH3. So meaning it has one NH3 on one end, another one here, another one here, another one here. So now the coordination number of this particular compound here we are seeing is 4. So sometimes if they form this coordination compound, this copper can form more than 4. It can form up to 6 from what I'm seeing on this configuration. But now, let me say it like this. This compound now, we are seeing it as Cu bracket open NH3, then having 4. Then it has 2 plus. These 2 plus should help you know. Just note something that it can collect 2 more. Two more other ligands. So if it's 1 plus, means despite the one it's already connected to 4 already here. It's connected to 4 here. It can connect to extra 2. So that's how you can use to get the coordination number. You check the total number of ligands circling or bonded to the central metal atom. So the central metal atom in this case is copper. So they could ask you in this compound here, what is the central metal atom? The central metal atom obviously is copper. In some other cases, you might see it as I think there's some coordination compound that is given as I think it has potassium. And it also has, I think it has another center atom. I don't know, I cannot really recall, but it has a center atom again. And that one is bonded to something else, to ligands, other ligands, and it has its own configuration. So the center atom is the one that is usually inside this square, the metal inside this square. Inside this square is usually the metal that is the central metal atom. So then now you now look at everything that is surrounding it, the total number of every single element, or every single ion, or every single molecule surrounding it, every single atom, every single ion, or every single molecule surrounding that central metal atom. If you count them, it will give you the coordination number of that coordination compound. So in this case now we can see that it is 4. The coordination number is 4 because it's 4 ammonia molecules that are surrounding copper. But it can take more than 4. But currently it's just 4. So I don't know if anyone has any question before I move forward. Does anyone have any question before I move forward? Can you guys hear me at all?
We good.
Okay. So now let's move on. So there are different types of ligands. We have different types of ligands. We have monodentate ligand, bidentate ligand, and polydentate ligands. So now these types of ligands is important to just take note of them, because I think these are the kind of things that they might want to just bring out as rough questions. I've not really seen it, but I just think they can come. It can come out if I was to set questions. The kind of things that was sitting on objective. So for ligands, monodentate ligand, they're the ones that have, they can donate one what they call is one lone pair of electron. They donate one lone pair of electron. So now for bidentate, it means they donate two, one particular molecule or one particular atom donates two lone pairs. So let me show you what it looks like now. Let me show you what it looks like. Or let me show you an example of what something like that looks like. So let's say we have this now. Let's assume we have this central atom bonded to monodentate ligand. It will have one of the ligand here bonded here with one teeth. Another one with another teeth. That is lone pair of electrons and bonded to it. Another one here. Another one here. Maybe another one here. So these ones are examples of monodentate ligand. You see all these attachments are just one attaching, giving one bond to this one. So now for a bidentate ligand, what it will look like is this. You will see something like this now. You would have one molecule that would bond here and here. Only one molecule would have two bonding sites. Only one molecule will have two bonding sites. So these examples, this kind of a molecule or this kind of ligand is called a bidentate ligand. That is just like meaning two teeth, a two-teethed ligand, a double-teeth ligand. So polydentate is one when you molecule being bonded at three spots or being able to form triple bond with the central metal atom. So an example of this bidentate ligand is something like CO2 or CO, sorry, carbon, what they call it, CO. That's C double bond O. It is looking like this. It's looking like this. You got something like H2 N double bond H, sorry, double bond N, double bond N, then H2. So this molecule is an example of a here and here. This center bond will disappear. This double bond here will disappear, but it's now used to form two bonds with the central metal atom. So that's how it forms. It forms this kind of bonding. So these are examples of bidentate, polydentate, and so on. So this is an example. An example is this molecule I just mentioned, H2N double bond NH2. H2N double bond NH2. So this is an example of a molecule that forms bidentate. Now that is this. That is the one I just wrote here. Ethylenamine. Another one is ethylenamine. Ethylenamine. This one here is an example of a bidentate ligand. So for monodentate, even ammonia is a monodentate ligand. Ammonia is a monodentate ligand. Chlorine is a monodentate ligand because it just uses one portion to get bonded to the central metal atom. So ligand bonding, where both electrons in the bond comes from the ligand. What am I even saying, sir? In ligand bonding, both electrons that is responsible for the bond formation comes from the ligand, which is what I just mentioned. I was talking about the types of ligand, and I said there are two types of ligand. We have the monodentate and the bidentate. So not really two, there are three types: monodentate, bidentate, and polydentate ligand. So these monodentate ligands, they are the ones that are bonded to the central metal atom or the central metal ion by just one bond. By just one bond, where one atom forms a single bond with the central metal atom. For bidentate, it means one atom or one molecule forms double bonds or two bonds with the central metal atom. So this kind of ligand, where the ligand donates two sets of lone pairs of electrons. That's what am I saying? We have a particular ligand. Let's say this ligand it donates a pair of electrons first, and it donates another pair of electrons next to the central metal atom. So this kind of ligand is called a bidentate ligand, where one single ligand donates two lone pairs of electrons. So that's what a bidentate ligand is. And an example is the ethylene diamine. And I was trying to mention another example, hydrazine. So ethylene diamine is an example of what they call it, is an example of this kind of compound. So how they form is that they would form bonds from their end, like this one. You see something, it will look like this. You will see probably C double bond, C bonded to NH2, NH2, NH2. Oh, no, sorry, NH2, we have here H, we have NH2 here, then H here. So now, what now happens is that this nitrogen, the nitrogen ends, is what it will now use to form bonds. So these two nitrogen ends that it has, it will now use it to donate electrons to the central metal atom. Let me put it here. Let me put it here. Let me put it on this end here. So just, can you guys still hear me? Hello, can you guys still hear me?
Yes.
Hello. Okay, thank you. So how it then forms is it will now use the nitrogen end and this nitrogen end to form a bond. This one will form a bond with the central metal atom. Then this one will also form another bond with the central metal atom, forming two bonds. This same bond is forming two bonds with a central metal atom. So this kind of ligand is called a bidentate ligand. So there are also polydentate ligand where one molecule will form several bonds with a central metal atom. So that's what these kinds of ligands are. That's what these ligand types help to tell. That's what they are. So now moving on to environmental chemistry. I was talking about green environmental chemistry. I said it is the portion of chemistry that is dealing with how what they call it, the environment, chemistry within the environment. Is one that talks about corrosion, pollution, and the rest. So we'll be starting this portion of chemistry with explaining what greenhouse gases are. So we'll be hearing greenhouse gases. We'll be hearing global warming. Some of us don't really understand what this thing means. So let me try to see whether I can give a pictographic view of what it looks like. So let's assume this is our earth here. This is our ground here. It's somebody on the floor. Somebody on the floor. We know that our earth has a firmament like this. So now, what then happens is this. How greenhouse gases happen is you would have these gases, usually methane, carbon dioxide, and even water vapor. They are examples of these greenhouse gases. What they do is that they will then leave the ground and go to the top region of the cloud, like their firmament, that blue region of our sky. These gases will go there and accumulate. They will just go there and pause there. They will stay at that region. And they will form a very thick layer, something as thick as this. A very thick layer covering towards the surface towards the atmosphere, the sky's frame. So now, what that happens is the sun our sun would then be bringing out its own heat. The sun will bring out its own heat from one side, trying to send heat towards the earth.
Hydrogen.
Yeah, can you hear me? Someone is saying something. Okay. So the sun will be giving off its own heat. So as this sun is giving off its own heat, these gases would be absorbing this heat. And as they absorb this heat, they become hot. And because of their hot, we under that these gases are blocking the sun from getting. The sun's what these gases will do, they will help us, they will prevent some kind of rays from getting to us, like UV rays from the sun. They will prevent them from getting to us. But now, because they are hot and they are around this our environment, it means we that are inside this environment will feel their heat. And that heat that we are feeling is what they call global warming. Because normally the temperature of the earth is supposed not to be that hot, but because of these gases, they accumulate so much in our atmosphere. They now trap. Yeah, he said.
Continue, boss.
Okay. So as these gases get accumulated on the sky, they trap this heat, and when they trap this heat, the heat will now be radiating towards us. The heat will radiate to the earth, and when the thing radiates to the earth, to start causing all these ice that are normally supposed to have been frozen, like in places like Antarctica and Alaska and the rest. The heat now will now be making them melt off. And these gases, not just that they don't supposed to be at this sky region, but now because of man-made activities, human activities that are releasing these gases in large quantity, the normal proportion that's normally supposed to accumulate around this region becomes thicker. It becomes thicker instead of the normal, maybe the normal size. Let's assume the thickness is supposed to be maybe, let me just use an hypothetical number that is not realistic. Let me say it's supposed to be maybe 1 kilometer thick. The gas thickness is supposed to be 1 kilometer thick. But because of several human activities and industrial activities that is happening so much, instead of 1 meter thick, it now becomes something like 7 meters thick. So that is completely abnormal. So when it becomes that, when that kind of abnormality happens, the heat that normally they're supposed to trap at that point will become more, and the heat that they will now be radiating towards us will become much more. And now it will now start altering some of the normal physical events or physical occurrences that are supposed to be in our earth. So that's what global warming is: the effect of these gases when they accumulate in our atmosphere. So as I have here, I said greenhouse gases, they are gases that trap heat in the Earth's atmosphere, leading to global warming. And I've explained what global warming is: the kind of warming that comes as a result of these greenhouse gases absorbing heat. The large quantity of these greenhouse gases absorbing heat and radiating this heat towards us on the Earth. So now, examples of these greenhouse gases: we have carbon dioxide, we have methane, we have nitrous oxide, water. But now water sometimes is not really considered as a greenhouse gas, but it's part of it, because water sometimes would fall down back as rain sometimes. But water is also water vapor. That's the better one to call it. Water vapor is an example of these greenhouse gases because it stores this same thing at the cloud. So now their sources where these greenhouse gases come from is from the burning of fossil fuels, from agriculture, and also from deforestation. So these are the sources of greenhouse gases. These are the sources of greenhouse gases. Agriculture, because when plants during photosynthesis, I think at night, plants, okay, during the day they take in oxygen and they give off carbon dioxide. So respiration is one of those things. But when you have large level of agriculture, there will be high volume of these gases like CO2 being released, and methane from some kind of combustion in engines, or no, not from combustion in engine, methane from some industrial processes or during some kind of fractional distillation of crude oil and stuff like that. Methane, like that, they get trapped in the cloud. So that's for that. So now some of the effects of this so acid rain is when it occurs when what they call it, when SO2, which is one of these greenhouse gases, and NO2 or NOx, that's any of the variants of nitrogen oxide, when it reacts with water vapor in the atmosphere. So when this kind of mixture happens, you will form sulfuric acid and nitric acid. So when you have sulfur dioxide in the atmosphere in large quantity and it now reacts with water vapor in the atmosphere, this reaction will then lead to the formation of acid, because normally SO2 and water vapor, if the SO2 becomes larger in quantity, it will form it will be able to form H2SO4 acid. And once it forms H2SO4 acid, when rain is falling, this is the kind of thing that will fall with the rain. So it causes a kind of level of acidity in our rain that's falling. I think there was a time in the past when they said acid rain wanted to fall in Nigeria. It actually happened, but just that the acidity was very, very low. It was very, very low. The rain was actually acidic, but the acidity was very, very low. So that's the reason why it was not really that disastrous. So another acid that can form is nitric acid. Nitric acid, when nitrogen oxide or nitrous oxide in any form gets mixed with water vapor. So that's how acid rain is being formed when there is a mixture between sulfur oxide and nitrogen oxide. You form acid rain. So this acid rain is what leads to sometimes you will see all this olden days zinc, all this our previous zinc, all this zinc material that is really zinc that they use zinc to make, they will rust faster because of when acid rain falls on them, they corrode, they experience corrosion, and when they experience corrosion, they will rust much faster than how it's normally supposed to rust. So once this kind of rain is prevalent, before you know, you will spend more money trying to change roof and change you put this kind of roof once, and before 1 year, 2 years, before 1 year, 2 years, the whole roof has turned brown and even started breaking because of continuous fall of this acid rain. Acid rain. Can you guys still hear me and see my screen?
Yes.
Can you guys still hear me? Okay. So now the damage that they do is that they damage ecosystems, they damage building, and they damage water sources. That's the disadvantage of this acid rain. I talked about ligands and I said the types of ligands we have monodentate, bidentate, and polydentate. And I said the monodentate ligands are the ones that have what they call it. They have just one bond where one ligand bonds with the central atom with just one bond. So for a bidentate ligand is when a single ligand bonds with the central atom with two bonds. A single ligand bonds with the central atom with two bonds. Then polydentate is when a single ligand bonds with the central metal atom with several bonds. Hello.
Hi. We can hear you, sir.
Okay. Okay. So now moving on. I then went into what they call. I said there are different examples of these bidentate ligands and their likes. We have, for examples of monodentate, chlorine, water molecule, ammonia. These ones are single monodentate ligands. But for bidentate ligand, an example is ethylene diamine. Ethylene diamine. So, and this is the structure which I drew here. So this is the structure of ethylene diamine. All this aside this point. Ethylene diamine. It's everything aside this portion. So now for this after that I went into this thing, environmental chemistry, and I said I was trying to explain greenhouse gases. And I said the greenhouse gases are gases that accumulate in the atmosphere and they absorb heat. They absorb it. They are gases that accumulate in the atmosphere and absorb heat so much that they will then cause a kind of heat in the environment, a kind of warming of the entire earth. So these gases they are known as greenhouse gases. And examples of these gases we have nitrous oxide, methane, and carbon dioxide. So how these gases accumulate, you will see them, they would be plenty. I was trying to draw a diagram before, and it's something like this. We have our earth, then we have our firmament, then these gases they will then occupy the topmost portion of this our atmosphere. So normally they should stay there, but now there's a quantity that becomes beyond normal. So how these greenhouse gases now, when they become normal, when they become abnormal, I mean, they then lead to what is known as global warming. Because when they become abnormal is when they become very, very high in quantity. And the reason for this their increased quantity or this their abnormal quantity is due to plenty human activity like agriculture, deforestation, burning of fossil fuel, and the like. So these events lead to the increased number of greenhouse gases. So when there is an increased number of greenhouse gases at the atmosphere, it causes the normal warming that's supposed to happen to become much more. So the earth will now become hotter than it's supposed to be because of there are more gases capturing heat. Because what happens in these gases is this: the sun would be somewhere outside our earth, shining its radiation towards the earth, as I was trying to draw before. And as the radiation is coming to the earth, these greenhouse gases normally they're supposed to be there to help cushion some of the effect of the sun ray, to absorb some of the sun's heat. So now, when they now become so much, the heat that they will then accumulate with themselves will become so much that the normal temperature that's supposed to keep the earth at will now become higher than the normal. So leading to what is called that global warming. So that global warming now would now be causing other abnormal events like the melting of ice in glacial regions and stuff like that. So that's why that's how the excess greenhouse gases is not really good because it can lead to global warming. And this global warming will expose our earth or our environment to some of the bacteria that are not really known yet since the times of Ice Age. If you've studied biology, you would probably remember they said, okay, at the beginning we had stuff like archaeas being the precursors of life, and they grew and grew and grew. They went through different levels of development. So during the Ice Age, there was a kind of disaster that happened where some of these organisms they got trapped, and evolution has happened. Humans have not been exposed to some of these kinds of bacteria. So if they now start getting freed by this time due to global warming, abnormal events, it would make our human system that is not yet adapted to this kind of thing experience a kind of new exposure, and it might lead to unexpected deaths because viruses that we are not really used to or our body system have not even been built to cope with. Once they attack us, our body might not even find resistance easily towards them. So that's why global warming is bad. Excessive greenhouse gas emission is not really nice. So that is for this. And I was saying that I said when this greenhouse gas, another adverse effect of this greenhouse gas is it can lead to acid rain because some of these greenhouse gases include sulfur dioxide, and nitrogen oxide. So when these nitrogen oxides are accumulating in the air, when they accumulate in the air, they can mix with water vapor. That's water, the heated water in the air. And once they mix with this heated water in the air, they can lead to the formation of acids like H2SO4 and even nitric acid. So once this is being formed, it will then cause the formation of acid rain, meaning that the rain now that will be falling now will no longer be purely neutral or normal rain, but now it will become acidic. And this acidic rain has its negative effects because it affects building materials like zincs. It will make them rust faster. It will make bridges corrode faster, rust faster at their base, and stuff like that. So these effects are not really pleasant to humans. So that's why excessive greenhouse gas emission is bad and is an environmental threat to humankind. So because of it can lead to these different scenarios. So now moving to nanochemistry now, I talked about the difference, how nanochemistry is the study of nanoparticles, how nanochemistry is the study of nanoparticles, and how these nanoparticles now they are formed. These nanoparticles, they are particles that are much more smaller than microparticles. Normally, microorganisms, microorganisms are organisms that are very tiny. You cannot see them with normal human eyes. So nanoparticles, they are much tiny that a single particle of nano or a single nanoparticle might not be able to visualize it with our normal eyes, and even with a normal simple microscope, you might not even be able to see the structure properly. So that's how these nanoparticles are. They are specialized particles that have unique characteristics. They are usually prepared in the laboratory through different synthesis procedures. So they have large surface area. So these are properties of nanoparticles. They have large surface area because they are very tiny in size. They have conductivity, good conductivity, and they are most of the times they are used for what they call it as better adsorbents, good adsorbent because of their characteristics of having larger surface area. So they are used for what they call it good. They are used as adsorbents. Another characteristic is that they are very reactive. They are very reactive. So these are the one of the major characteristics of these nanoparticles. So they are used in electricity. The study of nanoparticles is what is known as nanochemistry. Study of these particles and also their synthesis, that's their formation, their characterization, and their uses. So that's what nanochemistry is about, the study of nanoparticles, how they are being synthesized, their structure, that's their characterization, and also their uses. So now, these extra uses which I mentioned, using carbon nanotubes, they are used, there is an example of a nanoparticle, and it is used for electronics, it's used in electronics. I think it's one of the very, very important recent day energy energy reduction of the high level conductivity material, this carbon nanotubes. So they are also used in medicine for drug delivery system. They use these nanoparticles to coat drugs such as they would not go to an unprecedented location. The drugs, because normally when you take in drugs to your body, it will just dissolve into your body and the drug particles will then move to the regions where they are needed. Sometimes it might miss the targeted site. But now, by the result of this development of nanoparticles, these nanoparticles they could be characterized or created and made specific that they would specifically look for the targeted region by themselves. They will not join at any other point except they find that targeted region in the body.